Welcome, everyone. Let's get started. There are no course announcements today, except that the problem set is due this evening, so I thought that a puppy was maybe necessary. Bit of a stressful time for several reasons. Are there any questions? Puppies should be a part of more classes. Okay, let's get going. So, as a reminder, we looked at the standard form of a linear program last time, and we also very quickly looked at some motivation for the dual, but I think it was too fast. So I'm going to go through all the slides about the dual again, and more too. The standard form of a linear program has the optimization as a max, not a min. A linear program in general could have a max or a min. All variables are constrained by being greater than or equal to 0. All other inequality constraints are going to be less than or equal to instead of greater than or equal to, and there aren't equality constraints. And the last time we showed that we could get any LP, any linear program, into the form of a standard form just by turning it into an equivalent linear program. Okay. So suppose we have an LP in standard form. And this is the reason why we're going to be thinking about standard form is first for the dual, and then we're going to sort of use that a bit for the simplex method, though it's going to be a slightly different form. Okay, so suppose that, for example, we have this LP in standard form. Then this is just an example. We're maximizing this subject to these inequality constraints and assuming that all the variables are greater than or equal to 0. Okay. Now, we can work out some things about the optimum here. Let's try adding the first inequality constraint and 2 times the second one. So if you add the right-hand sides of these inequality constraints, or if you add this and 2 times the second one, you get 4 plus 2 times 10. If you add this plus 2 times this, then you get this and this. And so overall, you get the inequality 24 is greater than or equal to 2x1 plus 2x2 minus x3. That's what happens. You can just add, you can linearly combine inequalities. So it's just this inequality times 2 plus this inequality. Cool. Why does this help? We saw it last time, but let's look at it again. Why does it help? I'm trying to work out some things about the optimum of this objective function. So it's not the same as the objective function, but it's x2 more than the objective function. And so since x2 is non-negative, we know that the objective function, the objective function here is upper bounded by this, which is itself upper bounded by 24. And that means the objective function can't get bigger than 24. It might be less than 24. It's possible we can't get to 24. But at least we know it's less than or equal to 24, just by virtue of combining the constraints that we have. Questions? Why twice the second one? So I agree. We don't know how to get this magic thing, but if we could get it, then this would help us. If we could combine these constraints in some way such that we ended up with something that had greater coefficients than this. So for example, if we could combine them to get a 2 here and a 1 here and a 0 here, so 0 is greater than -1, that would also give us an upper bound. Or if we could combine it to give us a 3 and a 2 and a 1, that would also be an upper bound. It would be a less good upper bound. But any way that we can combine these to give us something where the coefficients are greater than here, or greater than or equal to, will give us an upper bound, if that makes sense. And here we just suppose it was just it's trial and error. We're trying to get an upper bound on a max problem, right? Because if we want to find a maximum of something, it helps us to know that it's less than or equal to something. We could also find lower bounds, and lower bounds would be just trying different values. And we know that it's greater than or equal to any particular value that we tried. But here, sort of the harder thing is trying to come up with an upper bound for a maximum. That make sense? The punchline is going to be that we're going to find an upper bound that works, an upper bound that is itself equal to the max. So a tight upper bound. Is it always possible to get an upper bound? We will see that in a moment. But yeah, so if you could combine the constraints in order to give you something that looked like that, it would give you an upper bound and you would be happy. We don't know yet that it's possible to do that. But in this case, the optimum is at most 24. It might be less than that. Okay. So this inspires us again to take a linear combination of the constraints to see how tight a bound we can find. So let's multiply the first constraint by y1, and then the second one by y2, and so on. In this case, we have only two constraints. We're only considering the ones which aren't the greater than or equal to 0. Okay? So what does it mean? What are we trying to do? Well, we're trying to multiply this constraint by y1, this one by y2, and so on. And what we would like is that the coefficient on x1 from combining this is going to be at least the coefficient on x1 here. Likewise, we want the coefficient on x2 from summing these two to be at least the coefficient in the objective function, and so on for all of the variables. So if the coefficient on xi in constraint j is aij, you can think of this like a matrix. And the coefficient of xi in the objective function is ci. Then we just need combining all of the aij with yj, because we're multiplying constraint j by yj. We just need that is greater than or equal to ci. That's what we want. We want to find y1, y2, and so on that gives us this, because that would give us an upper bound. We also want all of these y's to be greater than or equal to 0. Why is that? Well, it's just because we don't want to flip any of these inequalities. We never want to multiply a less than or equal to by something negative, because then it would turn into a greater than or equal to, and we wouldn't be able to combine them. So we want this condition to hold. We also want this condition to hold. And what are we trying to optimize here? Well, we would like the best upper bound. We'd like to have an upper bound, but we'd like it to also be the best one. And what is the upper bound? Well, the upper bound is combining all of these. So in this case, it was 4 plus 2 times 10. So in general, it's going to be the sum of bj, which is these things, times yj, which is the things we're multiplying by. So we want to satisfy these and minimize this for some setting of the yj. That really looks like a linear program. Find some yj that are minimizing this subject to these constraints. And again, we want this to be as small as possible, minimizing this. So this is the dual linear program. We started out trying to maximize this thing. These are just the coefficients and the constraints. I've rewritten it as c.x. c.x is just the same as any linear combination of the particular variables x. Subject to, these inequalities, and ax less than or equal to b is just the same if a is a matrix and b is a vector. Just the same as if we took these bj's to be the components of the vector here. And the aij's to be just the coefficients on these x's here. So here it would be like 2, there's a 0 implicitly for x2. 2, 0, 1, 0, 1, negative 1 would be the matrix A in this case. So you can rewrite the general linear program in standard form like this. And then given that, we can rewrite the dual, or we can write the dual, as just what we did on the previous slide, minimizing this sum, which is just b dot y, such that A transpose y is greater than or equal to C. That's because of this. The transpose comes because we're multiplying by yj instead of by yi here. And then y is greater than or equal to 0. You can look up how to get the dual if it's not in standard form. It's pretty easy to work out yourself too, but I'm just going to assume that the linear program is in standard form. So what are some things that we notice here? Well, we're optimizing in the original LP, we're optimizing for some x in r to the n. In the dual, we are optimizing for a y, but y is not in r to the n. Y is in r to the m. What is m? Well, m is the number of constraints. And that makes sense because what we're doing is we're trying to find a linear combination of the constraints. So the y's are the things we're multiplying by all of the constraints. So you have n original variables, m constraints. In the dual problem, you have m variables. And how many constraints? Well, how many constraints do we have in the dual problem? We have n constraints now, not counting these. Because this is a matrix equation. A transpose is going to be n by m because A was m by n. So we're going to have n different constraints here. And that makes sense because going back to here, we have a constraint corresponding to each one of these x's. We needed to know that the coefficient on x1 from our linear combination is greater than or equal to the original coefficient on x1 in the objective function. So we're going to have a constraint for each one of our variables in the original problem. So we're swapping out the number of constraints and variables. Started out n variables, m constraints. Now we have m variables, n constraints. Also, we started out with a max problem. Now we have a min problem. The greater than or equal to 0 is still greater than or equal to 0. Also, this is no longer less than or equal to. It's a greater than or equal to. So a few of the things switch out, not all of them. In particular, the x greater than or equal to 0 and y greater than or equal to 0. That's the thing that stays the same. But everything else sort of flips. Questions? So this notion of a dual is going to turn up in many places in mathematics. And it doesn't mean the same thing. Like, well, not all duals are connected, but they sort of all have the same general principle in that you can sort of transform something to the dual version of it. And then the key point about duals is if you take the dual of the dual, then you get something special. So let's see what happens in this case. If we have the dual of an LP, we say that the original LP is the primal. So we can say that there's a primal and then there's a dual of the primal. What is the dual of the dual? Yeah, it goes back to the primal. And this is something you hope is the case in duals. So let's see why this is the case. Suppose, again, the primal is this. I've just rewritten it, the same thing. Maximizing ax less than or equal to b, x greater than or equal to 0. The dual, again, is minimizing for a different number of variables. B dot y, swapped b and c here again, notice. Number of the vector here becomes the vector here becomes the vector here. Okay. So how do we even compute the dual of this? This is not in standard form. So we need to change it to standard form, but we know how to do that. We can just negate this, so it's now the max of negative of this, such that the negative of, we're just taking the negative of both sides. And now this is less than or equal to. OK, great. Now we can compute the dual of this. OK, so what's the dual of this? Well, we know that max is going to become min. This vector is going to swap with this vector. This vector is going to be transposed. And this is going to become a greater than or equal to. So we have minimum of negative c dot x such that negative ax greater than or equal to negative b. And that's just the same as the primal. We can compute, we can flip the inequality just like we did and get back this constraint. We can flip the objective just like we did here and get back this and get back that objective function. So it's exactly the same as the primal. Questions? OK. Now, here we're getting into sort of the reason why all of this dual stuff is useful. Suppose we have a primal problem. This is just the same as before. Dual problem, same as before. Let's call the primal problem P and the dual problem D. Suppose you have a feasible point. Again, a feasible point, remember, is something that satisfies all the constraints. So you forget about the objective function if you're considering just a feasible point. Suppose that it's just like something that satisfies these constraints. Suppose you have a feasible point for P and a feasible point Y for D. Then we have c dot x, the objective here, is less than or equal to b dot y. So anything that you're trying to maximize this, you're trying to minimize this. Anything for the primal is less than or equal to anything for the dual. It's sort of like the dual is coming down and it's trying to get as low as possible. The primal is coming up and trying to get as high as possible. You might wonder how close these two are. But this is the theorem that all of the things for the dual are above all of the things for the primal. OK. How can we prove this? Any thoughts? We have a lot of equations here and a lot of inequalities and constraints. If I'm trying to prove something like this, I just start writing out things that I know. I'm just going to write out some steps here. So we know that c dot x. Remember, we're trying to prove something about c dot x. So what do we know about c dot x? Well, c dot x is, another way to write it is x transpose c. The dot product of two vectors is the same as transpose of one times the other. So c, we know, is less than or equal to a transpose y. And so we can actually write x transpose c is less than or equal to x transpose a transpose y. Now, why is that? Normally, we can't do this sort of inequality thing with dot products. But in this case, we can, because a transpose y is greater than or equal to c, and x is greater than or equal to 0. So entry-wise, this works out, if that makes sense. Every entry, every single one of those scalar products in the dot product that is being added up here is greater than. This side is greater than this side. OK, so now what do we do? We haven't got all the way to b dot y. We need to show that this is less than or equal to b dot y. Hopefully, it's less than or equal to b dot y. Yeah, so we do the same thing using the other constraints. We have this thing, we can rewrite it as AX transpose times Y. That's just because this, move the parentheses over here, you get AX transpose times Y. Now, AX transpose is another vector. So AX transpose times Y is just, again, this is a dot product of vectors, but we can actually say it's less than or equal to B transpose Y. Why is that? Well, for the same reason as here, Y is a positive vector or non-negative vector. AX is less than or equal to B. So the dot products work out. And we have a less than or equal to. And so combining all of that, we have C dot X is less than or equal to this, which is less than or equal to B transpose Y, which is just the same as B dot Y. Questions? Confusions? What is not clear here? Ah, great question. We'll get to that in a moment. Okay, so first corollary of this. If you have a primal that is unbounded, so C dot X can get really big, as big as you want, then D has to be infeasible. Why? Well, because if we had a Y that was a feasible point, it would have to be bigger than all of these. An objective function bigger than all of these. But if this is unbounded, then it can't exist. So if P is unbounded, then D must be infeasible. Similarly, if D is unbounded, i.e. this can get as small as possible, then P must be infeasible because there can't be an X here. Now, suppose that both of them are feasible and they have optima. X star in the case of the primal and Y star in the case of the dual. Then, from this, we have that the primal solution is less than or equal to the dual solution. Right? That's just from this weak duality result. Is there a way that we can use this theorem to show that they're actually equal? I know I looked at this and I thought, oh, well, because the dual of the dual is the primal, that means that obviously you can just swap them and then you get that these two are equal. That is unfortunately not true. Or rather, this statement actually is true, but we can't just use the dual of the dual as the primal argument. Let me give you a quick indication of why you can't just use the dual of the dual of the primal as the argument. Though this, again, this statement is true. If they do have both optima, then they are equal. I'll get to that in a moment, but let's try using this dual of the dual thing. So if we were to rewrite the dual as, again, the max of negative b dot y, and p is the min of negative c dot x, then we can apply the theorem again, since p is the dual of d. And in that case, we would have that negative b dot y star is less than or equal to negative c dot x star from this result. But if we take negatives, then unfortunately the inequality sign flips as well. And so basically the point of this is, and don't worry if you're not getting this, but if we try to flip the primal and the dual, then we get the same result actually, because there are negative signs on these. And so it tells us exactly the same thing. Weak duality does not give us strong duality. Again, if you didn't get this slide, don't worry about it. Don't worry about it. However, it is actually true that if they both have optima, if they are both feasible and they both have optima, the primal and the dual, then the objective functions are the same. This is sort of the point of the dual. And it's really cool. If you have a linear program that is about maximizing this thing, there is a dual linear program which is about minimizing this thing, and they come together exactly at this point. Every solution, every feasible point for the primal is below here, every feasible point for the dual is above here. And they come together at exactly the right point. Unfortunately, it's too long and complicated to prove here, but you can go into a proof. It's not so bad, but just not time during class. So again, possibilities for the primal and dual. P is unbounded, in which case D is infeasible. The dual is unbounded, in which case the primal is infeasible. They could both be infeasible, in fact. Or both of them are feasible and bounded, and they have the same optimum, which is a max in the case of the primal and a min in the case of the dual. Are there questions? Don't have a strong intuition for why only one would be unbounded. Again, going back here, if we had one of them unbounded, then suppose the primal is unbounded. Then you can take x such that c.x is really, really big. It can just keep on getting bigger. You can pick x that is above 1,000 so that c.x is greater than 1,000. So you can pick x so that c.x is greater than 1,000,000, 1 billion, and so on. That means, by this theorem, weak duality, that if y is a feasible point for the dual, then b.y has to be bigger than all of those. It has to be bigger than 1,000, but it also has to be bigger than 1,000,000 and 1 billion and any number that you pick. But it can't be bigger than any number. And so there can't be a y. So if p is unbounded, then d has to be infeasible. And similarly, if d is unbounded, then p has to be infeasible. Thanks for the question. More questions. Okay. Why is the dual useful? Just really quick indications of this. So first of all, it helps us to just understand linear programs. Like, we have a better sense of the math. In certain cases, a linear program may be much easier to solve in its dual form. So if you convert it into the dual, you can just solve the dual instead of solving the primal, and that will give you the same answer if they're both feasible. Another thing is the dual sort of provides a certificate of optimality, in the sense that if you have a primal and a dual solution, like two feasible points of primal and the dual, and they are the same, then you know that they're both the optimum, because any solution to any feasible point for the dual is greater than any feasible point for the primal. And so if they ever are equal, then you know it's the optimum for both of them. Questions? Okay. To certify the optimality, do we need to find both? Yes, you would need to find both. Couldn't they meet at more than one point, e.g. a plane? Yes, but that would show that all of those points are optima. Though I wouldn't think about it like a plane, because x is an n-dimensional point and y is an m-dimensional point. So it's that the objectives are the same, not that they don't actually live in the same space. Primal and dual are different. They're different spaces. They have different numbers of dimensions, y and x. Okay, so now let's actually get into a way for solving linear programs. And this is going to be too fast, unfortunately, just because of time constraints. I'm not expecting you to get all of this, and we're not going to go into all the thorny details of the simplex method. But this is just to give you a sense of how one would go about it. So suppose we have an LP in standard form, like this. Let's introduce some slack variables to make those less than or equal to constraints into equal sign. And I apologize, I realize that I actually should have converted this x into x in r to the 5. I apologize. Yeah, this is just a different way to write this down. x4 and x5 are non-negative numbers, so they just sort of captured the slack. Like, how much is this less than or equal to 4? Well, it's less than or equal to 4 by some non-negative number. This one is less than or equal to 10 by some non-negative number. So let's just put those in. It's going to be the same linear program. Okay. And this is just the same thing. I'm just moving it to the other side. Hope you feel convinced that this is just literally the same thing. Just move to the other side. Okay. Now this is our new thing that we're trying to solve. First of all, is it feasible? Is there a feasible point? Again, that's one that just satisfies all the constraints. Don't have to worry about the optimum. Can you just find a feasible point? Like, what is a feasible point? Do you have an example? Yeah, so I mean, there are several options, but one obvious feasible point is just literally setting this equal to 4, setting this equal to 10, and setting all the others equal to 0. Because clearly this one's satisfied, and these two are also going to be satisfied. OK. What's the objective value at this point? This particular point. It's just 0. All of these things are 0. OK. Let's try improving the objective. So starting out at this feasible point, let's improve the objective. Maybe we can increase x1. x1 looks pretty good in the objective. Maybe we can increase x1, and that'll add something to the objective function. Can we just increase x1 as much as we want? Yes, there are these equations here. So we're going to have to make sure that we keep these equations satisfied. So we increase x1 from 0 to c, and we're going to have to decrease x4 and x5. And if we decrease them too much, then they become negative. So that's a problem. So we start with x4 equal to 4, x5 equal to 10. So we have some sort of slack here. If we increase x1 to c, then we have x4 equal to 4 minus 2c, and x5 equal to 10 minus c. So we can increase x1 all the way up to 2 before x4 goes negative. OK. So let's see what that sort of translates into. We're going to set x1 equal to 2, and so now x4 is equal to 0, and also x5 decreases. Let's rearrange the set of equations to sort of reflect that. So this is where we were to start with. What this basically means, in order for us to sort of depict this setting x1 equal to 2, what we're just going to do is move it over to the other side. So we're swapping these two. This is the same equation. And then let's divide by 2 to make it the same equation again. And then what we have here is we have x1 equal to 2 minus this. And now the idea is that if we set x3 and x4 equal to 0, then x1 is equal to 2 minus 0. And so this is sort of how we have set x1 equal to 2. And then we're going to substitute this into both of these other places where x1 occurs. So this is just, we've just rearranged the equations. Clearly, we have a set of equations that is completely equivalent to the previous ones. It just done some substitutions. But now, if we simplify, this is just simplifying, what we have is a set of equations where the obvious solution is x1 equals 2, x5 equals 8 now, x4 went to 0. It's now on the right-hand side. All the things on the right-hand side are going to be 0. But the objective function also went up. Because we did this substitution, remember here we started out with this. We knew we could increase x1 to 2, and that would cause x4 to drop to 0. If we increased x1 to 2, that would also increase the objective function to 4. And indeed, now the objective function is 4 plus 0 plus 0 plus 0. So what we've just done is rewritten everything in such a way that the obvious solution, where all of these are just equal to the constants and everything else is 0, it makes it very clear that we have an objective value of 4. So now our provisional solution is 2, 8, and all zeros. And the objective is, again, better than 0, which it was before. Now it's 4. This is called a pivot. We have an entering variable, x1, which is the thing that got increased. It was previously 0, now it's 2. And we have a leaving variable, x4, which was previously non-0. It was 4 previously, and now it's 0. And what that basically meant is just we swap x1 and x4 here, and then substitute in everywhere else so that x1 is now no longer anywhere but here. Are there questions about this? Are leaving variables always on the right-hand side? Yeah, the leaving variables are going to end up on the right-hand side. They move from the left-hand side to the right-hand side, and the entering variables move from the right-hand side to the left-hand side. You're always swapping one from each side. Just sort of makes it easier for us to keep track of them. OK. Let's do this again. We're trying to increase our objective value. Maybe we can increase it some more. How can we do that? What should be the entering variable? And why? What should be the entering variable? Ah, yes. OK, so the entering variable should be x2 because it has to have coefficient greater than 0 in the objective function. If we increased x3, we would make the objective function actually smaller. And we can't make x3 smaller because it's already at 0. x4 is also already at 0. So nothing we do to x3 and x4 will make our lives better. x2 can make our life better in this particular way, assuming our life is measured by this LP. So we pick x2 as our entering variable. Whoops, sorry. What is our leaving variable? We want to swap x2 somewhere on the right-hand side, swap it with something on the left-hand side. In this case, it's easy. There's only one equation with x2 and x5. We're going to swap x2 with x5. Previously, we had two options, actually, because there's x1 was appearing here and here, and we had to pick the one that was going to go to 0 first. But here, no, we just pick, there's only one option. So here, we started out, sorry. Yeah, sorry, this is just me. I already swapped the two. If you swap these two, then you end up with this. And then just substituting in for x2 here. And that's what the pivot is. Again, what we started out with was here. We moved x2 to this side. We moved x5 to this side. If necessary, we rearrange, but here we don't even need to rearrange. Then we substitute in for x2 up here. Simplify, and we're done. Okay, that was another pivot. Our provisional solution is now 2 and 8 and zeros. Can we make it any better? Can we keep on pivoting? No, we can't. Because these are all negative. The coefficients here are all negative, which means that any solution here has to be less than or equal to 12. And that's a proof, right? We basically proved it. The max has to be 12 because, you can never do any better than 12. Because we're trying to maximize 12 minus 3 things that we know have to be non-negative. We're subtracting something that is clearly non-negative. So the best that we could do is by making all of these 0, which in fact we are doing. And so we've got the optimum, which is 2, 8, and all zeros. There might be some other ways to attain that optimum, but we found the optimum value. You don't even need to appeal to convexity. This is literally a proof. The max is, we're looking for the max of 12 minus some non-negative things. 12 minus some non-negative things can be at most 12. Okay. Other questions about this example of the simplex algorithm? Simplex method. It's called the simplex method or the simplex algorithm. And if you're wondering why it's called the simplex method, it's frustrating. It doesn't actually involve the simplex. There's some historical reasons for it, but it's not very good. You're looking for a geometric intuition. We will get to that. Okay. Do we prove that this gives us a maximum? We prove that if we stop, then we do not, then it has to be a maximum. And that's because, again, if all the other coefficients here are negative, we know that whatever is in the constant term has to be the maximum because we know that 12 minus something non-negative has to be at most 12. Because we're subtracting non-negative, like this is just literally a way to have rewritten the original problem. Any solution to the original problem has to be also a solution to this and vice versa. It's not like it's not like we've set anything equal to individual values. We're provisionally thinking of x1 is equal to 2, x2 is equal to 8, and all the other things is equal to 0. But this is just literally another way to rewrite the original linear program. And so maximizing this objective function is literally equivalent to maximizing the original one. And so if this is 12 minus something that is greater than or equal to 0, then the original has to have an objective function that is at most 12. What would have happened if we had picked the wrong entering variable? We will come to that in a bit. Okay, so what is this simplex method, like in general? What we did was we used slack variables to rewrite the linear program. We had all variables greater than or equal to 0. We had equality constraints instead of less than or equal to. We had variables on the left-hand side sort of provisionally being non-zero, the variables on the right-hand side being provisionally 0. But we swap what we're thinking of as on the left-hand side as on the right-hand side. Take an initial feasible solution just by reading off the constants and the equality constraints. Like here we were reading off like 2, 8. We pivot by increasing an entering variable on the right-hand side and decreasing a leaving variable on the left-hand side to 0. And by increasing it, I really just mean that we're rearranging these equations. We're not actually setting these variables equal to anything. We're just moving things around. We're swapping between we're swapping between things on the right-hand side and things on the left-hand side. We're just literally rearranging these equations. But it changes our provisional solution because it changes these constants. So we choose an entering variable with positive coefficient in the objective because we know that increasing the entering variable is going to give us a better objective. We choose the leaving variable as the first variable that would decrease to 0 as we increase the entering variable. And then we rewrite the equations in terms of the new right-hand side variables, sort of swap things around, and then we sort of do a substitution. And then we just repeat until there are no more positive coefficients in the objective. And that is the algorithm. Now, there are various objections, various issues that might arise. Let's look at the issues that might arise. First of all, the biggest issue is initialization. So we got lucky here. We said 410. What could go wrong? We assumed we had a feasible solution. What could have gone wrong with that? Negative constants. Yes, we could have had -4 there, for example, instead of +4. That would have sucked. So I'm not actually going to deal with this problem. But suffice it to say, it is a problem. We can't just set x4 equal to -4 because we know x4 has to be non-negative. All of them have to be non-negative. So we need a way to reorganize the linear program so we can start at a feasible solution. And there is a way to do that. And it actually involves basically sort of weakening all the constraints so there is a feasible solution and then gradually tightening them. And the way that you do this is you use the simplex method actually to tighten them and work out how tight you can get and work out if the problem is infeasible. Because it's possible, remember, some linear programs don't have a solution at all. They're infeasible. So in some cases, we won't be able to find a feasible point, but there's a way to use the simplex method to do that. And I'm not going to go into that. But basically, the idea is if we can find a place to start out at, the simplex method will take us from there to the optimum. The second thing was something that somebody asked. We might have a situation where a new entering variable, where it doesn't help us, for example. If it doesn't increase the objective. For example, here with x1, if you change this to a 0, swapping x1 and x4 would actually not increase the objective at all. x1 and x4 would both stay 0. So you might worry that you could keep on pivoting forever without reaching the optimum. You could keep on swapping things around, but you're not actually increasing sorry, I shouldn't have said optimum, increasing the objective. You're not actually, you're without reaching the optimum. Yeah, you could keep on pivoting forever without ever increasing the objective, but not actually reaching the optimum. But there is a way to fix this. For example, there are rules for picking which entering variables to choose if there's any ambiguity about it. For example, you could pick the xk with the smallest value of k out of all the possibilities. And this will end up not looping. You can prove that you never end up getting into a loop where you keep on cycling forever, and you're eventually going to have to reach the optimum. There's a question about, is there an analogy to turning up the temperature on an energy-based method, weakening and tightening the constraints? Yes. Sometimes, here's the third problem. Sometimes a pivot will allow us to increase a variable as much as we want. This is not really a problem. It's just, it is an indication that there isn't an optimum to the linear program. So for example, this was what we were looking at. But if I change these to plus, then if we want to increase x, we can just do that. We increase x1, we increase x1 here, have to increase x4, but we can keep on increasing x4 as much as we want. We increase x1 here, we can keep on increasing x5 as much as we want. We never have to actually, there isn't a way to do the pivot because there is no bound on how much we can increase x1. In that case, we see that we end up with an unbounded linear program. There is no optimum. So it's feasible, but it's not bounded. And the simplex method will allow us to discover that. OK. Now, finally, let's look at the geometric interpretation of this. In the simplex method, remember, we had n original variables. Then we add m more variables, one for each of the m less than or equal to constraints. So we had a total of m plus n variables. The m more variables were the slack variables, remember. So we had m plus n constraints greater than or equal to 0. Like constraints of that form, sorry, I should have said. And we had m equality constraints. At each step, we have n variables equal to 0. So n of these greater than or equal to 0 constraints are tight. N out of these. And all of the equality constraints are tight at every point. So for every one of our candidate points, we have n of them equal to 0, n of the coordinates equal to 0. We have m equality constraints tight for. So there are a total of m plus n tight constraints out of a total of 2m plus n constraints that could be tight. Let's consider the polytope of feasible points. Remember, the vertex of a polytope is a point with the number of tight constraints equal to the dimension. So for example, if you were in 2 dimensions, then you have a polygon. And the number of constraints that are tight at a point, at a vertex of the polygon, is 2. So if you're on 2 of the edges of the polygon, then you're a vertex. Likewise, if you're in 3 dimensions, say you're a cube, if you're on 3 of the faces of the cube, then you're a vertex. Because you're in 3 dimensions. If you're in 4 dimensions, then you're on 4 of the facets, then you are a vertex. So if you have the number of tight constraints equal to the dimension, which in this case, the dimension is m plus n, because there are m plus n variables. And in the case of all of our candidate points, they have m plus n constraints tight. Some of them being greater than or equal to 0 constraints, some of them being the equality constraints. So what we have, actually, is we have every one of our points that we're considering being a vertex of the polytope of feasible points. We can think of the simplex method as starting at one vertex of the polytope and just moving from one vertex to another one. Each vertex is on a set of bounding hyperplanes. And each pivot is just swapping one tight constraint for another. You're saying, previously, this one of the hyperplanes was tight. Now I'm going to swap that hyperplane for another one. And that corresponds to getting a new set of hyperplanes and taking a trip along an edge to a neighboring vertex. So you're walking along the edges of the polytope to a neighboring vertex. And you're basically walking in the direction of increasing the objective function. So this is the intuition that you should have geometrically for how you are getting to the optimum. Remember, we knew last time that the optimum of a linear program has to be a vertex, or has to be achieved at a vertex of the polytope of feasible solutions. So we're just walking along all the vertices, or walking along some of the vertices, trying to find the optimum one. This also sort of indicates why you're eventually going to find your way to the end, because you just keep on trying a bunch of vertices, and you keep on getting better each time. You're going to eventually reach the end. There are other ways of solving LPs. I'm not really going to talk about them. Some of them involve moving through the interior of the polytope instead of going around the outside of the polytope or the surface of the polytope. For example, Kamar-Karr's algorithm. And they stay inside the polytope sort of until the last moment. It's like cutting through the polytope instead of going around the edge. There's the ellipsoid method where you sort of convert it to a problem of just finding a feasible point in a different linear program, and you gradually find a feasible point in your polytope by making smaller and smaller ellipsoids containing the polytope. But I'm not going to actually go into details on that. Next time, we will get started with graph algorithms. Have a good weekend, everyone, and good luck if you're finishing the problem set. Here's a quick poll about the timing of the class, and I will stick around to answer any questions. Thanks, everyone.